All right, so we're going to continue looking at section 6.1. Okay, so yesterday we left off with how to convert between radians and degrees. And today we're going to learn a formula that requires angles to be in radians. All right, so we're going to be given word problems, and they might not give us the angle in radians. It might be in degrees. But to answer the question, we're going to have to convert it to radians. Okay, and the word problems are going to focus on what's called arc length. All right, so we already talked about what an arc is yesterday. Okay, it's when you have an angle in a circle, and the two rays of the angle hit the edge of the circle, and if you connect those points, you have an arc. Okay, so here's a circle. There's an angle drawn inside the circle. Where those two rays intercept the circumference, that is an arc. Okay, right there. So what do you think it means when I say that the size of the arc and the size of the angle are proportional? They're not the same, unless you're on a unit circle and you're measuring in radians. Then they are. But in general, if you're just on a generic circle, the size of the arc and the size of this angle are proportional. What do you think that means? Well, what does it mean in general if two things are proportional to each other? What does that mean? Well, Zach, any idea?
Like, as the angle increases, the arc length increases at a similar rate?
Yeah, basically means if you change that size of that angle, the arc changes at the same rate. So if you were to double the size of this angle, what do you think would happen to the size of this arc? It would double the length of the arc. If you make this angle half as big, it would make the corresponding arc half as big. Okay, so that's what it means that they are proportional. We're going to come back to that idea because it's going to allow us to set up a proportion. Right? So arc size and angle size are directly proportional. All right, so what I've drawn here is similar to the other diagram, except I've drawn two angles. Okay, I've drawn theta. It's a Greek letter theta. And the arc corresponding to theta is S. And I've also drawn theta 1. And the arc corresponding to that is S1. All right, now, in order to come up with a formula to figure out the length of an arc, we've got to have a starting point. Okay, we've got to have a fact that we already know is being true, a relationship between arc size and angle size. Okay, and I gave an example yesterday. If you wanted to convert feet to inches, you would have to already know that there are 12 inches in 1 foot. Okay? And then if you said something like, I have 49.6 inches, how many feet is that? I just have to solve that proportion. Okay? But I have to already know this fact to start. Okay? If you don't know one fact at least, you can't figure out anything else. Okay? Same idea here. We have to already know a fact. And yesterday I gave you something that I said we're going to come back to, and now we're going to come back to it. If you make this angle a certain size, then it causes something special to happen if you compare the arc length and the radius length. Does anybody remember from yesterday how big this angle would have to be? And then there would be a special relationship between the size of that arc and the length of that radius. Well, does anybody remember what the special relationship is? This usually doesn't happen, but it can happen if you compare the length of the radius and the length of the arc. What can happen if you compare those two numbers? They could, yeah, they could be the same length. And they are the same length if you make this angle a certain size. What did we say yesterday? This angle would have to be. And the arc and the radius would be exactly the same.
Would it be 1?
Yes. So that's kind of our starting point. We're going to use that fact, just like we could use there's 12 inches in 1 foot. If you make this angle exactly 1 radian, okay, then what happens is the size of the arc and the size of the radius are the same. And we can use that one fact to figure out anything else we want. Just like we can use that one fact, there's 12 inches in 1 foot, to figure out anything else you want. Right, so any questions on that idea? If you make that angle 1 radian, S1 and R would be exactly the same. All right, so now what we're going to do is set up a proportion, and then once we set it up, we're going to use that fact. Okay, but we have to set up a proportion, something we can plug into first. All right, so set up a proportion. And anyone think they could give me a proportion using these 4 values? Theta 1, S1, theta, and S. And there's lots of ways to set up the proportion, but as long as you're consistent, okay, like I was here, inches, feet, you just have to set it up the same way on both sides. So anyone think they could set up a proportion with those 4 values I circled? Yep, Dave?
S1 over theta 1.
Okay.
Divided by, equals, and then theta over S.
So you weren't consistent on each side.
All right, so then S over theta.
Right. If you put arc length in the top, angle in the bottom, arc length in the top, angle in the bottom. Right, so that works. Okay, and the reason, again, you can do that is because arc length and angle size are proportional, so you can set up a proportion. Now we're going to plug in that fact that we know. We're going to fill in our starting fact, and then we'll figure out a formula. All right, so our starting fact is that S1 equals R. So let's change S1 to R, and theta 1 is 1. Okay, that's your starting fact. Now on the right-hand side, we're just going to leave both of these blank because we don't know what we're plugging in. Okay, so just leave them as variables. S over theta. And now you could leave your formula just like that, or you could simplify that proportion. And how do you simplify a proportion? Yep, Allie? Yeah, cross multiply. So we have S times 1 equals R times theta. And that is your arc length formula. S times 1 is S equals, and then R times theta, it's just R times theta. So in that formula, you've got 3 variables. Okay. S is your arc length. R is your radius. Theta is your angle. But you've got to be careful about your angle, and I mentioned this earlier. It has to be in radians. Okay, the reason why it has to be in radians, we assumed way back at the beginning we were working in radians. You don't have to derive the formula the way I did it in radians, but if you do it in degrees, it gets a little messy because you have to have a 360 and or a 180 and a pi in there. The formula in radians looks cleaner. That's why I'm doing it in radians. Right, so there's really 3 types of problems they can give you with this. They'll always give you 2 out of 3 of these letters and ask you to find the third. Okay, they could ask you to find the arc length, the radius, or the angle. Okay, we'll practice, we'll do a couple different types. Okay, And in order to do these problems, you really don't need a diagram, but I just drew it so you could visualize what the word problem is saying. They want you to find the length of an arc that's in a circle. The circle is a radius of 2 inches. And the angle that forms the arc is pi over 4 radians. Okay, so what's my formula? Let's just write that down so we know what we're plugging into. Yeah, go ahead.
S equals R times theta.
S equals R times theta. Okay, and they're telling me find the arc. Okay, so I already know I don't know S, so I must know everything else. Okay, what do I fill in for R? Amanda? Yep, R is 2 times, and what's my angle? Pi over 4, and it's already in radians. I know that because there's no circle on it telling me it's degrees. Okay, so pi over 4. And now just multiply straight across and reduce what you can. So when I do 2 times pi over 4, I get 2 pi over 4, which reduces to pi over 2. And in fact, this isn't approximate. This is the exact answer. Okay, if I type this into the calculator and round it, then it's approximate. Okay, so the approximate answer is 1.57. Now, because this is a word problem, we need a label. It's pi over 2, or 1.57 inches. Okay? We just found S. S and R are the 2 length units in the problem. So you just have to look back up and see what did they use for length. The only thing that's not measured as a length unit is theta. That's radians. Okay, so it's pi over 2 or 1.57 inches. Okay, any questions on that? Does anybody know another way you could find that arc without that formula? Just trying to use a little common sense and being clever about it. Because there is a way to do it if you don't know that formula. Yeah? Yeah, it has something to do with the circumference and the information that's given up there. Anyone have a thought? Yep.
Another way to do it in geometry, we should set up a proportion where you have arc length over the degree measure equals the total circumference over the entire area.
Which would be how much? Yes. So you could set it up that way. Basically, it's like you're finding percentages, right? If you had a circle, okay, like that, and let's say that this angle was 10 degrees and this radius is 4 inches. Well, I can find the circumference of that circle because I know the radius. And then I could figure out what percentage of the circle does that arc take up. How do I know that? Well, this arc is formed by an angle of 10 degrees. That's 10 degrees out of a total of 360. So I'm taking up a little less than 3% of the whole circumference. So if I knew the whole circumference, I would just have to multiply it by 2.8%, or 0.028, and that would tell me how much of the arc I have. Okay? Same thing like if you had this. If you had a 90-degree angle, that takes up a quarter of the circle. 90 out of 360, it's 0.25. So if you knew the whole circumference and then took a quarter of it, that would tell you the arc corresponding to a 90. So you can figure it out without the arc length formula, using a proportion or a percent, but I think the arc length formula is faster. You know, because you don't need to set up a proportion. You just have to multiply 2 things together. No cross multiplying.
So if you did it the way that Ali said, wouldn't you have to change the gradient, like
It depends how you set up the other side of the proportion. She said 360 to go all the way around. You could substitute 2 pi instead, and then it would work. Yep. But as long as you keep all your units matching, either degrees or radians, you're okay. All right, let's try this one. It says, find the radius of a circle if the arc length is 3 feet, or 3 pi feet, and the central angle is 60 degrees. Okay, so again, my formula is S equals R theta. And what is the letter they're asking me to solve for here? R. So that I don't know. What can I fill in that I do know right away? Okay, let's start with S. What would you fill in for that? 3 pi. And now they do give us some other information, but I don't agree that it's directly theta. What do I have to do with it? I have to convert it. So off to the side, how do I convert degrees to radians? Pi over 180. You don't have to reduce it, but it will make it a little easier when we have to type it in. What does 60 pi over 180 reduce to? Yeah? It's pi over 3. Okay, now I want to get r by itself, but I'm multiplying it by a fraction. So how can I move pi and 3 to the other side at the same time? Yeah, Tom? Yeah, multiply by the reciprocal. 3 over pi and 3 over pi. So the 3's are gone, pi's are gone, and now you have r by itself. And what is r going to equal? Yeah, it's going to equal 9 what? Feet. Okay, r is the other unit that is a length measurement, and lengths were measured in feet in this problem. Okay, so there's an example solving for r instead of s. Any questions on how you would do an example solving for theta? They'd give you the s, they'd give you the r. I mean, all you have to do is this. Take s divided by r, and that will give you theta. But any questions on that last type? Okay, so I'm going to hold off on doing that one. So the last thing we're going to look at in 3.1, as I already said, is angular velocity. Does anybody know where? Well, I already asked if you've heard of it, but I said you've all indirectly heard of it, or probably even used it, or said things that are measured in angular velocity. But can anybody think of an example of something that is measured in angular velocity? I'll give you a hint. It measures motion on a circular path. So something going like this. Anybody think of where you might use that? Yeah?
The Earth around the sun.
Okay, so when we talk about a year that is revolving, the Earth is revolving around something, 365 roughly days in a year. What's another thing you might use? I'm thinking of something that's not revolving, but something that's still moving in a circle but staying still. Well, it's moving, but its center point is stationary.
A clock.
Okay, so like the hands on an analog clock, we could measure the speed of the second hand, how it's moving at a certain speed. What else? What? What about cars? What?
Tires.
Okay, what about the tire? They spin, but there's 2 ways to measure the speed of a tire spinning. One way is to say miles per hour, which is not angular velocity.
Revolutions per minute.
Revolutions per minute. Okay, so if you've got something spinning in a circle, okay, a lot of power tools are measured in RPMs. Your cars, like engines, so I asked you about what about cars, like the engine of a car. The tachometer measures the engine speed in RPMs. But now there's a question, why? Why do you need RPMs? Why can't you just measure speed the way we always do? Just measure it in like miles per hour or feet per second. Okay, why can't you just use that all the time? It's what?
It doesn't move.
Well,
Well, it moves, but it doesn't go anywhere. It's stationary.
okay, so it is kind of revolving around a fixed point. But how about, let's say, think back to like the planet example. Let's say you had a rope, and on the end of that rope you tied an object, and you started swinging it in a circle. So now it's, so like a rock or something. So now it's moving. Everything's moving. It's not staying stationary. That rock is moving. There's a reason why I can't measure it in miles per hour. Okay, and there's a hint kind of in this diagram. Okay, so I've got 3 dots, which I'm going to make 3 different colors. And I'm going to take and just bring this around 1 time. Okay? And if you watch what happened, the black dot, I put it as close to the center as I could. So what did you notice about the black dot? It didn't really move. If it was exactly in the center, it wouldn't. And then how about the red dot and the green dot?
They stay the same distance away from the center.
Okay, they always stay the same distance from the center.
The green dot moved the most.
The green dot moved the most. Okay? Even though they all just went around 1 time, the green dot moved the most if you were to trace the path that it moved. Kind of thinking like about an orbit around the sun, right? Planets further away move the most. Planets closer to the sun move the least or have the quickest orbit in general. So, but now the green dot moved the most. We all agree on that? Now, if you compare the time it took the red dot to go like that and the time it took the green dot to do the same thing, how do the times compare?
They're the same time.
They're the same time. Okay, so now we run into a little bit of a problem. If one object is moving farther than the other, which everyone agreed, the green dot is moving farther, but it's doing it in the same amount of time, what does that mean about the green dot? It's moving faster. Okay? And the problem here is that every dot from the center to the circumference, they're all moving at different speeds. So it would be very confusing to try to describe the speed of the red and the green dot in a linear way. And that's what this formula is. Okay, that's linear speed. All right? So if we just say something like, these dots did 1 revolution in 2 seconds, then they're all moving at the same speed. They all did 1 revolution in exactly 2 seconds. The size of the revolution is different, but not the revolution itself. Okay? So that's why they use RPMs. Okay? So we can say every dot is moving at the same angular speed. Right? So angular speed, you can measure it in either degrees, radians, or revolutions. Those are the 3 units we use. If the book doesn't specify what unit to use, you always, in this class, we'll use radians. Okay, so that's kind of the default. So you'll see some problems in the homework tonight that say, find the angular speed of something. And you're like, well, wait, what unit do they want me to use? Use radians if they don't tell you. Now, as far as the time unit, I don't care what time unit you use. If it's in minutes in the problem, use minutes. If it's in seconds, use seconds. Okay, but always default to radians per time unit, unless they say otherwise. Okay, so comparing that to linear speed is the speed of an object that's moving in like a straight line. Okay, think of that, that's measured in like miles per hour. There's a distance component and a time component. just like angular speed, except the distance component in linear speed is something that you'd use like on a tape measure. It's feet, inches, centimeters, miles, okay, things like that. So what we're going to try to do is convert between units. Okay, we'll start out with very simple conversions, conversions that don't have two components. Okay. Speed is a rate. Rates have two components. 1, 2. We're going to start with something even simpler. Okay. We'll just start with something like example 7a. Okay. Convert days to minutes. Just days to minutes, just one component. And then we'll build up to something that's a little harder. Convert 50 feet per second, which has two components to it, to miles per hour. Okay? Now, you can learn all kinds of formulas and tricks to do it, but I think the easiest way to do it, so you don't really have to memorize different formulas, is just to do dimensional analysis. And that's how I taught you how to convert between degrees and radians. Okay? If you want a unit to cancel, just put it in the opposite spot. Right? If you've got inches in the top and you want it to cancel, put it in the bottom, and they cancel out. Okay? So that's how we'll do it. All right. So let's start with 3 days. Okay. In order to do this, you have to know the conversions, basic conversions in your head. Okay, so you have to know how many seconds in a minute, how many feet in a mile, how many inches in a foot, things like that. All right, so as you convert, basically you just go 1 unit at a time. Okay, we're trying to get days down to minutes. Right? So what's the next unit that's smaller than a day, heading towards minutes? Yep. Yeah, we're going to go to hours.
24 hours over 1 day.
So there's 24 hours over 1 day. Okay? And the reason I put day in the bottom is because I want it to cancel days in the top. So always put the unit that you want to cancel in the opposite spot. Okay. Now I want to get from hours down to the next smallest unit. So what's the next unit smaller than an hour? A minute. Okay. Now, where would minutes go and where would hours go? Minutes in the top, and then hours in the bottom. Okay. So now, what's the conversion between hours and minutes? 60 minutes and 1. I guess it's really just hour. All right. So we have days. It's going to cancel. Hours is going to cancel. And what's the only unit left?
Seconds.
Minutes.
Minutes.
I thought you meant to do next. I was like, okay.
All right, so now just multiply everything across the top. 4,320. Thank you. Okay, and if you had a denominator, you just multiply everything that's in the denominator and divide by it. Okay, so any questions on how we converted days to minutes? Okay, now in the next problem, that's only going to be half of what we have to do. We're going to convert a time unit, but then we're also going to convert a distance unit as well. Okay, so we'll do both. So what does this rate mean? 50 feet per second. You travel 50 feet every 1 second. All right. So now our goal, we got to figure out which unit we want to change first. Do you want to get seconds to hours, or do you want to get feet into miles? It doesn't matter. No. Okay, so we're going to get feet into miles. Even if you don't know the conversion, you should know where feet are going to go. Okay, feet are going to go in the bottom. What goes in the top? And now we do need to know how many feet in a mile. 5,280.
580.
Now, what if you stopped right there? What's the answer? What's the units in this problem?
Miles per second.
Yeah, we have miles per second. Okay, we want miles per hour. So now, same thing we basically did in the last problem. Change the time unit. We're trying to go from seconds to hours. Okay, what's the next unit up from a second? A minute. Where is minutes going to go? Top. Seconds?
No, back, other way. Other way.
Okay. Thought someone said minutes in the
I was
top.
in the next step.
And then seconds would go to the top. Okay, what's the conversion there? 60 seconds in 1 minute. Okay, now if we stop here, we have a speed in miles per minute. And what's my last conversion going to be? 60 minutes in 1 hour. Okay, now I'm going to look at my units, make sure I'm left with the right ones. Miles, hour. Okay, sometimes people write it as MPH, or you can just write it as miles/hour. Right, same thing. All right, so we've got 50, oops. We had 50 times 60 times 60. 60 times 60 is 3,600. 3,600 times 50 gives me 180,000. And then divide by 5,280. Okay, so 50 feet per second is about 34.09 miles per hour. Okay, any questions on that one? All right, so the last one we're going to do, and you know what, I think let's just go right to 7D, or example 8, is going to involve converting between a angular speed and a linear speed. All right? So this one has 2 parts. They want me to convert RPMs, which is what I'm given, into radians per second. And the reason I skipped the last one is because it's basically the same thing, converting between RPMs and radians per second. So we're going to do the reverse of what we would have done in 7C right now in 8A. So it's almost the same thing. And then we'll do part B in a minute. All right, so 1850 RPM. What does that mean again? Yeah, that's how many revolutions we're making in a minute. All right, I want to convert to radians per second. Well, I can start with 60 minutes. Whoops. In 1 minute, 60 seconds. Okay, so now I have revolutions per second. So now I got to get from revolutions to radians. Where would revolutions go? Even if you don't know the numbers yet, we should know where it goes. Yeah, it has to go in the bottom, and radians would be in the top. So now what's the connection between radians and revolutions? Well, let's think of it this way. What's the connection between degrees and revolutions? Amanda? Yeah, there's 360 degrees in one revolution. So now tell me that same fact, but just tell it to me in radians. Convert 360 degrees to radians. Yeah? Yeah, 2 pi radians in 1 revolution. Okay, so for this one, what we could do is, because it has pi in it, you can leave your answer as an exact multiple of pi, or we can round it. We'll just round it off. So 1850 times 2 times, now on this calculator I don't have a pi button, so I'll just type it in. type. So times 2 pi, and then divide by 60. Okay, if you have your pi button on yours, just press that. Okay, so what is the units on that number?
Units?
Yeah.
Do you read?
Yeah, it's 193.73 radians per second. All right, now we're going to do part B. Okay, find the linear speed of a point on the circumference of this wheel. So in other words, in that diagram I drew with all the different points on it, I want to find the linear speed of a point that's right on the circumference. Okay. Another way to think of this is if this tire was spinning at 1850 RPM and you put it on the ground and it didn't lose any traction at all and it just took off, how fast would the tire be going? Okay? That's basically what we're figuring out. So we'll see what happens. So to figure that out, it's actually helpful to go back to what they gave us. Part A doesn't help us to do part B at all. Okay? So let's look at part B. So we're traveling at 1850 RPMs, and they want to know what that would be in feet per second. Okay, what's one thing I can do first to try to get it into feet per second? This part is the easier part. Yeah, I would just convert minutes to seconds. Okay, and we've already done that before. In 1 minute, there's 60 seconds. Now I've got to make the jump between angular and linear. Okay, I have revolutions. I want to convert revolutions to something else. So where would revolutions go? In the bottom. Now I'm going to go and look at my distance unit and see, does it match what they want? They want feet. Okay, let's go back and look at the problem. Did they give me feet in my word problem? No, they gave me inches. So what I'm going to have to do is go to inches first, because that's what I'm given, and then I can change inches to feet. Or I could change 18 inches to feet right now if I wanted. Either way. Let's just leave it in inches and we'll change it to feet after. So I need a connection between inches in a revolution. How can I figure out how many inches in a revolution? Well, Taylor, any thoughts how you can figure out how many inches in a revolution? Well, think of it this way. If you have an object that's round, okay, and you mark it and it starts at a certain point, okay, and then you roll it, along until it hits that point again, and then measure the distance it just rolled. What is that distance that it just rolled on the table? It's the circumference of the thing that rolls. Okay, so as long as we can figure out the circumference, we can figure out how many inches in a revolution. So what's my formula for circumference? Yeah? It's 2 pi r. And now they told me, I got to be very careful when I read it. The radius is 18. What if they said the diameter? What would you do to that number? Yeah, so just make sure you catch that, because that's a mistake a lot of people make. Make sure it says radius. Okay, so your circumference is 2 pi times 18, or 36 pi inches. There's no reason to do that out. Okay, just leave it. So 36 pi inches in a revolution. 1 revolution. And now the last step, they said they wanted feet, not inches. So how many inches in a foot? How many? 12, yeah. Okay, so now inches is gone. And I'm left with Oh, revolutions is also gone. Feet per second. Any questions on how you'd finish that up? You just have to multiply 1850 times 36 times pi, and then divide that whole thing by 60 times 12, or 720. Okay? Any questions on that? What's different about this conversion? This conversion is very different than any of the other ones. In fact, it's different than every other conversion we did in every other problem today. Yeah?
Because it's like pi and 36 and then the others are just like.
Well, we did have some that had a number with pi, but it's a good guess. But we had some that had a number with pi. But there's another reason why it's extremely different. Yeah?
It changes depending on the problem.
This conversion changes in every problem. Right? How many seconds are in an hour? How many feet in a mile? Those kind of conversions never change. But how many inches in a revolution? Well, it depends if your tire is something small or if it's a car tire or something even bigger. Okay? So you can't always assume there's that many inches in a revolution. You have to figure it out every time. Okay? All right, so any questions on that idea? Right. Now, what if you had a problem that said an object, let's say this object rolled 1,000 degrees. Find out how far along the ground it rolled. What might you want to do with 1,000 degrees first? Because that's not really helpful. It's easier to think of degrees in a different way.
Would you like set up a proportion to like 1,000 over x equals 1 over 60?
Yeah, so you're basically converting degrees to how many times it revolved. Okay? So if something went 1,000 degrees, that means it rolled 2.8 times. Right? So if you knew the circumference of a revolution and you know it went around 2.8 times, what would you do with 2.8 and the circumference? Do what? Yeah, you just multiply them because it made 2.8 revolutions. Okay, so you might see a problem similar to that as well. Okay, find out how far an object rolled along the ground, assuming it went a certain number of degrees. Okay, but same idea. All right, so last thing we'll take a look at. We're not going to get into it too much today. Is unit circle trigonometry. So I wrote out what the whole idea of unit circle trigonometry is. So I'll say it first, and then if anybody really wants to write it, you can. But the whole idea of unit circle trigonometry is you draw an angle with the center right at the origin. Every angle has an initial and a terminal side. Well, when you draw that terminal side, it will hit the edge of the circle somewhere. And the whole goal is to find the coordinates of that point. Okay, that's unit circle trig. Find the coordinates for where the end point hits the circumference of the circle. Okay, and that's basically what I wrote right there. Okay, so for certain angles, you can draw them in a unit circle. You can sketch it, and then find where the end point hits the circumference of the circle. If you can find the coordinate, the x and the y value are what allow you to do unit circle trig. Okay, so any questions on that idea of unit circle trig? Now, I said certain angles, okay, because we're only going to do angles on a unit circle that are multiples of 30 or 45. Okay, we're not going to just, if it's an angle that's not, we'll use a calculator. Okay, but by certain angles, I mean angles that are multiples of 30 or 45. All right, so now we're going to look at, for the first time in this class, the 6 trig functions, and we're going to define them in terms of the coordinate for where the terminal side hits the end of the circle. Okay, so our 3 basic functions we deal with are sine, cosine, and tangent. Okay, and I put the abbreviations below them. And if you want the sine of an angle, okay, first thing you'd have to do is draw the angle. There's your angle right there. That's probably like 140 degrees roughly. And then I'd have to find the coordinate. Once I have the coordinate, if all I want is the sine, I just need that number. That's the answer to the sine. If I wanted the cosine, okay, well, this time I don't need the y value. I would need the x value. So the sine basically has to do with how high up is that point above the x-axis. Okay? So you might see that there's another angle that would have exactly the same sine as this angle. Okay? There's some other angle that would have its terminal point right there, which would almost be like a mirror image. We'll talk about that. And the sine of those 2 points would be the same. Okay? And the last one is the tangent. Okay, to do tangent, you have to find the y value and divide by the x. And I didn't mention it for cosine, but you could think about this one the same way. There's another point that has the same x value as this one. It's that one. All right? And again, if you draw that angle in, it's like a mirror image. Okay, so this idea of having a mirror image, it's going to help us out a lot tomorrow. All right. Now there's 3 other trig functions besides sine, cosine, and tangent. You don't have buttons for them on the calculator, so we don't use them as much, but we still can use them. Does anybody know the other 3 trig functions besides sine, cosine, and tangent? Yep, secant is one. Cosecant. And cotangent. Okay, and I put their abbreviations right below it. The only abbreviation that's a little tricky to remember maybe is cosecant, because every other trig function just uses the first 3 letters. But you can't for cosecant, because we already used cosine. So they just break it up into the syllables. Co-se-cant. Now, does anybody know the relationship between sine and cosecant? It's the same relationship between cosine and secant and between tangent and cotangent. So by opposite, you mean put a negative in front? The reciprocal, yeah, you flip it. Okay? So if you know the sine, if you take that value and flip it, that's your cosecant. So what would your secant be? Yep. And what about your cotangent? X over y. Okay. But the way we're defining them, you have to be able to find the coordinate. If you can't do this. So you might have done it as like opposite, adjacent, and hypotenuse before. This is the same thing. Okay, and once we do opposite, adjacent, hypotenuse, I can show you the connection, but if you draw a triangle out of it, which we're not really getting into a triangle right now, but if you did, you have opposite, adjacent, and hypotenuse, and it comes out exactly the same. Okay, does everyone have those 6 formulas? Okay, if you have an angle that lands right on an axis, either 0, 90, 180, or 270, those are called quadrantal angles. Because they land on the axes, which divide the plane into your 4 quadrants. And now these are basically the 2 steps to do unit circle trig. Okay, 2 steps are very simple to understand. 1, find the coordinate. 2, plug the coordinate into the formulas. On the test, the way I'm going to do it is I'm going to ask you for 1 out of the 6. I'm not going to ask you for all 6 of these in the same problem. Okay, I might say something like, tell me the cosine of 90 degrees. And that would be a question. Or I might say, what is the cotangent of 270? Okay, but the way I'm going to practice it right now with you is I'm going to do all 6. Okay, we'll find the sine, the cosine, and so on. Now, in step 1, it says find the point. Sometimes the point is given to you. Okay, in example 1a, they give it to me. And in example 1b, they're going to give me the coordinate. So if they give it to you, you've already done step 1. The only thing you have to do is take the x and the y value and plug them into the 6 formulas we just had. Now, when we do one like that, they're not giving you the coordinate. They're telling you 90 degrees. So first, find the coordinate for 90 degrees, and then plug it in. And it's not very hard to find the coordinate. All you have to remember is, what kind of circle are we on? Unit circle. And visualize that diagram in your head. Okay? To get to 0, 90, 180, or 270, all you're doing is moving 1 unit right, up, left, or down. So just think what the coordinate would be if you move 1 unit in any of the directions I just said. All right, so let's start with this one. Even though they didn't ask us, does anybody know what that is the coordinate for? What angle? 0, 1? Yeah? Yeah, it is the coordinate for 90 degrees. You don't have to know that in this problem. Okay, the goal is not to find the angle. The goal is to find the sine, the cosine, the tangent, and so on of the angle. So let's start with sine, cosine, and tangent. Okay, so we're not finding the angle, we're describing things about it. Okay, it's kind of like if you met someone on the street. You don't need to know their name to describe things about them. You can describe the color shirt, their hair color, their eye color. You can describe characteristics about them without ever knowing the actual name of the person. Okay, we don't need to know the actual name or size of the angle. Okay, so what's the sine of this angle? Yeah, the y value, which is 1. How about the cosine? And the tangent? 1 over 0. And what is that? Undefined. Okay, how about, what's the reciprocal of sine? Which trig function? Cosecant. And what do you get if you flip 1? Think of 1 like this. You get 1. 1 is one of the 2 numbers that you can flip and it doesn't change. There's another one as well. Well, let's try it. So the secant, think of 0 like this. 0 over 1. When you flip it, what do you get? You get 1 over 0 when you flip it. And what's 1 over 0? Undefined. And what about the cotangent? When you flip it, you get 0 over 1. And what's 0 divided by 1? 0. So the only one that's tricky is when you flip 0, you get undefined. When you flip undefined, you get 0. Okay, and this one worked out nice because there really wasn't a lot of arithmetic. Okay, and this one, we have a little bit of arithmetic we're going to have to do when we go through it, but nothing we haven't done before. All right, so let's start with, what's the sine here? Yeah, square root 3 over 2. You don't have to do any decimals. Okay, just leave fractions. Quinn, what about the cosine?
Would be
1/2. And the tangent is y divided by x. And the way I visualize it, square root 3 over 2 is y. 1/2 is x. I just imagine putting a division line in right there, and that's tangent. What happens when you divide root 3 over 2 by 1/2? Or how do you do that? How do you divide root 3 over 2 by 1/2? Yeah? So it would be root 3 over 2 multiplied by 2 over 1. And what happens? Yeah. So when you're dividing two fractions that have the same denominator, the denominators just cancel each other out. Or you can flip and multiply by the reciprocal, and you'll see the same thing. So we get square root of 3. What's my cosecant? Two over the square root of 3, which is a good first step, but I don't like that as a final answer. How come? Because it has a square root in the bottom, and we usually get square roots out of the bottom. If you ask yourself why, it's really not important to do it anymore, because it goes back to when calculations were harder to do without computers and calculators. It's very hard to divide by a square root. That's why they got it out of the bottom. But now with the calculator, there really isn't as much of a point, but they still do it. So we'll do it here too. What do you multiply by to get that square root out of the bottom? Square root of 3 over square root of 3. So in the top, I get 2 square root of 3, and in the bottom, 3. Okay, how about my secant? Would just be 2. That's an easy one to flip. Just 1 over 2, flip it to 2 over 1. And what about my cotangent? I would look at our 1 over the square root of 3. And what would you get? Square root of 3 over 3. Okay, so anytime you get a square root in the bottom, just make sure you clean it up and put it in the top. Okay, and these last ones are pretty much the same. So let's try 90. What's different about this problem? What did I mention earlier? Okay, it's in degrees, but what's different about it from the previous two? You don't have the coordinate. So that's your first step. Graph 90 and find the coordinate. Yeah, the coordinate is 0, 1, and we already did that problem. Okay, so all the answers to example 2 are from example 1a. The only thing you had to do first was find the coordinate. Okay, what about 270? What's the coordinate for 270? Yeah? 0, -1. So it's going to be almost the same thing as 90, except everywhere you had a 1 for y, just change it to a -1. And then go through the problem. Okay, but that's your first step, find your coordinate. How about pi? What could be a little harder about this one? Why is it a little harder this time? Maybe for some people. Maybe that isn't harder for other people. But why could it be harder? Something different about it. Yeah? It's radians. If you're not familiar with radians, it might be harder to find the coordinate. If you are, then that's just as easy as the last two. But what could you do if you don't know what this is? Pi. You could convert it. And how would you do that? Yeah, you just multiply by 180 over pi. So pi radians is 180 degrees. What's the coordinate for 180? Yeah? -1, 0. It's right there. And now you go through and plug in all the x's and y's into those formulas. Any questions, or does anybody need me to do that out? Okay, so just be careful when you work with the quadrantal angles, because one of the coordinates is always going to have a 0 in it. And if you divide by 0, that's undefined. I've seen a lot of people put divide by 0 is 0. No. Divide by 0 is undefined. 0 in the top of a fraction, that's okay. But 0 in the bottom is always undefined. All right, so the homework, the first part is on 324. And I want you to try 56 to 61, 70 to 73. And then on 335, there's only 3 problems in the book. Okay, 1, 5, 8. But I want you to do what they're asking you to do in 1, 5, and 8. So just read the directions. And I want you to find the sine, the cosine, the tangent, the secant, the cosecant, and the cotangent for 1, 5, and 8. Okay? And these other 3 problems I'm giving you here. Okay, so you've got 1, 2, 3, 4, 5, 6 problems where you're going to find sine, cosine, and so on. Okay, so there should be 36 different answers for page 335. But they don't take long to do. Okay, they're just the ones and the zeros. Right? Okay, so we'll look at that tomorrow. Tomorrow we will finish up everything in section 6.2. Don't forget my extra help. It'll be on Wednesday because the test will be on Thursday.